Okay, today I'd like to talk to you about the use of mantle normalization diagrams to understand the behavior of TeAsBiSb and selenium to deduce the effects of sulfide segregation, crustal assimilation, and degassing in mafic and ultramafic lavas. First of all, what are the TeAsBiSb? Well, we introduced this term to refer to tellurium, arsenic, bismuth, antimony, and tin. And the reason we introduced it was there's no good chemical term to cover these elements, and they are the most common essential components in PGMs. So we needed a term to cover this group. And we see these elements ending up with the platinum group elements at the end of fractional crystallization of a massive sulfide liquid. Here's an example from Norilsk. We also see them as exsolutions, platinum exsolution. Here's a spherulite exsolution in chalcopyrite in both reefs and massive sulfides. And then we also see these platinum group minerals frequently around altered sulfides. So we interpret them as residual, that sulfur is mainly dissolved, and we're left with the PGMs fixed by these TeAsBiSb. But to better understand the geochemical cycle of the TeAsBiSb, we wanted to know what is the concentration of these elements in mafic and ultramafic magmas from which the sulfide liquid segregates. So how do we go about this? Well, we determined TeAsBiSb in mafic and ultramafic lavas where we already had a whole rock major, trace, and importantly, PG analyses. And these are the various places we happen to have in our collection that would give us some rocks. The other thing we did was I should emphasize the concentrations of TeAsBiSb in basalts and the crust are very poorly defined because of the analytical difficulties of determining these elements. They're present only at the ppb level. If you use ICP-MS, there are interferences on many of the elements that cause trouble. And also, when you want to dissolve the rocks, they're very volatile. So if you're using standard dissolution techniques, you often lose quite a few of the TeAsBiSb. So we used a method proposed by Pitcairn originally, which is hydride generating followed by atomic fluorescent spectrometry. And this gives us all of the TeAsBiSb except tin. And as a bonus, it gives us selenium, an element we're always interested in. And we checked that our analytical method was working well by looking at a range of ordinary rocks, ordinary crustal basalts and rocks published in geostandards. So once you've got the data, what then? We decided after a while, one way we can look at this is if you think about the TeAsBiSb, they're essentially incompatible with silicates and oxides. So they should behave like incompatible elements. So at one end of the diagram here, I put tantalum or niobium, you could use zircon, and that is to control the effects of partial melting and crystal fractionation. Then we added thorium next door. Thorium is also incompatible, of course, but it concentrates a lot in the continental crust. So it's going to give us a signal when there's crustal contamination, continental crust contamination. Then the TeAsBiSb and a few other chalcophiles that are incompatible are plotted in order of their partition coefficient into a sulfide liquid. So why did we add the copper, palladium, and platinum, apart from the fact we happen to have these results? Well, that is because these elements are considerably less volatile than the TeAsBiSb. So that could give us some control on whether we've got degassing. Degassing, of course, is considered very important for those people who study major extinctions in LIPS projects, in LIPS provinces, but also if you're trying to estimate the composition in the basalt and you use a LIPS basalt, as you'll see, you'll probably get the wrong answer. Advance, please advance. Okay, so what did we find? Well, especially for Mike, here we have Cape Smith, and we have, if we look at the basaltic komatiites, they're approximately flat at 2 times mantle. So we're not looking at sulfide segregation, and we're not looking at crustal contamination here. And the basalts overlying them are also show similar patterns. We've got slight enrichment of bismuth here. So that's the simplest possible case. Okay, what happens when we segregate sulfides? What we have over here is a pattern for N more. The purple is our results, and the gray are results from the average from the literature. And what we see is the pattern is essentially flat from thorium through to selenium, and then we have a steep drop-off, tellurium and PGs. And it's long been acknowledged that the platinum and palladium, low platinum palladium in more, is due to the segregation of sulfides, these little sulfide droplets you find in more. And I emphasize here, it has to be a sulfide liquid. You can't just leave MSS behind in the mantle, because MSS or ISS will not accept palladium, platinum, and tellurium. And here, the interesting thing on this diagram is that you can also see the effect of tellurium on tellurium. You could ask, why don't the other chalcophiles go down? Well, that's because of their lower partition coefficients. What I've plotted over here is the bulk D assuming cotectic proportions of sulfide segregation as we go across our diagram. And what we see is it's only when we get to tellurium that we see a reasonably high bulk D. So we only see the sulfide segregation in more on its effect on the chalcophiles at tellurium. What happens if we have crustal contamination? For crustal contamination, I've used the B1 dikes of the Bushveld, shown here in red. Now we know from other work that these dikes have had, dikes and sills and marginal rocks, they have had 15 to 30% upper crust contamination. We can model it by an AFC process to get this, the isotopes and the major and trace elements. So we applied that modeling to Komatiite contaminated with continental crust. And what you see, the continental crust is enriched in thorium, arsenic, antimonite, and bismuth. So it pulls up the thorium and those elements, and that you get this slightly wavy pattern. And if you want to see the details of the modeling, you can go to Eduardo's paper in Lithos. What happens when we go to the large igneous provinces? We're interested in the concentrations here because we often talk about the nickel sulfides and the late intrusions as forming from magmas formed in large igneous provinces associated with plumes. So here we have the Emission basalts and picrites. We have both the low and high titanium picrites. And what we see on the pattern is a steady decrease from thorium through to palladium, but a remarkably large negative selenium, tellurium, bismuth, and arsenic anomalies, which we attribute to degassing. And I was puzzled at first. I couldn't understand what was happening with the antinomy. Why was the antinomy still roughly online? So I was delighted to find a paper by Selzinski, Journal of Volcanology Geothermal Research, where he's measured partition coefficients of the elements between vapor and basalts at Alta Ali and at Kamchatka. And what he finds is indeed arsenic, bismuth, selenium, and tellurium partition very strongly into the vapor, but antimony, copper, platinum, palladium have not partitioned into the vapor. And for the people who like to study mass extinctions, you can get some idea of how much you've lost by looking at where these elements would have been on the line here. And it seems that we're losing 80 to 90% of most of our tabs. The Karoo will give you the same sort of answer, except here we can see the effect of crustal contamination as well because the thorium goes up. Again, we're losing 90 to 75% of our tabs. indica, which is the equivalent of the Piranha basalts in Brazil. We say it's the same type of thing. Interesting, you come to the Siberian flood basalts, and I have to admit, I do not have many samples. We do not have many samples. But since they look like the ones where we have lots of samples, I think it's fairly safe. What we see from the lavas, from the upper part of the pile, the KH and MK series, we see, as we do in the other LIPS provinces, some influence of crustal contamination, thorium enrichment. We see arsenic depletion, bismuth depletion, tellurium and selenium depletion. So we think that's due to the degassing. When we come to the Nijinsky lavas, the Nijinsky lavas, which are some workers, myself included, think that probably the sulfides that form the Noros deposits segregated from these lavas. What you see is, if we compare the pattern we have for the lavas that don't show depletion of platinum and palladium, we see that the Nijinsky lavas are extremely depleted in platinum, palladium, tellurium, and the other chalcophile elements. And we lose sight of our degassing signature a bit because there's so much influence for the sulfide segregation. Some cautions. Metamorphism, unfortunately, screws everything up. So if we look at mantle serpentinites here, you see that serpentinization in particular tends to enrich the rocks in arsenic, antimony, and bismuth. You see the nice big arsenic, antimony, bismuth anomalies there. And much to our disappointment, when we looked at our komatiites from the Abitibi, they're in greenschist facies, their patterns look all right, roughly all right, from platinum through to copper, roughly flat. They're roughly in line with thorium and tantalum, but arsenic, bismuth, and antimony are all enriched, which we're assuming is due to serpentinization. Don't really have time to go into this, but I would just mention it. Stop me anytime, Marco. Here we are at the Mariinsky. Sorry?
Nothing. How could I? You have still a few minutes.
Okay. This is the Mariinsky, the purple. And we can take the B1, B2 mixture from the Bushveld and model what we have using an R factor of around 30,000. The rocks have about 2% of these sulfide liquids and about 20% silicate liquid we need to put into it. And we get a pattern that resembles the Mariinsky rocks. Stillwater, I haven't got around to modeling Stillwater. I just put the green line on here so you can compare it with what's at Mariinsky. One thing I would like to mention here is the PGE to TeAsBiSb ratio is very much greater than 1. So we don't think that the TeAsBiSb are particularly important for collecting PGEs when we're collecting the sulfide. That doesn't, the TeAsBiSb go into the sulfides and they will eventually gang up or get together with the PGEs during exsolution or crystal fractionation of the sulfide liquid, but they're not the major motor of collecting the PGEs. There's just not enough TeAsBiSb to go around. Some cautions. Here I have the Platte Reef, and this is not our data. I just took the data from the African Mineral Standards. They issue standards all the time of ore deposits, and they've got quite a few from Anglo American's large mine on the Platte Reef. And here, what you may be seeing is two things. The country rocks are not necessarily always the same. So you can have when I've done the modeling, or we've done the modeling so far, we've just used the average upper crust, but we will get local effects. So as Hol was pointed out some time ago, the PGM vary along the Platte Reef. I think Cawthon pointed out the same thing along the Marinsky. It's true at the Great Dyke, and it's true at Sudbury. So the tabs will vary a bit depending on what you've mixed in. There's also the R factor effect. So there's our flat reef, and we can see we've got too much arsenic and antimony relative to our Marinsky. We can sort of model it by using a lower R factor, but I couldn't satisfy the antimony this way. So you need to do something more there. And so the tabs are incompatible. Concentrations can be estimated using other incompatible elements. The tabs are chalcophile, but only tellurium is affected when you just have cotectic segregation of sulfides. Thorium, arsenic, antimony, and bismuth are enriched in continental crust, so that leads to enrichment of these elements if there's crustal contamination. Thorium to tabs ratios can be used to estimate the tabs contents, in this case, because they will be increased. Subaerial basalts are depleted in arsenic, bismuth, selenium, and tellurium on mantle normalized plots, which we attribute to degassing. And be careful in metamorphic rocks because these elements are fairly mobile. Thank you.